So what I have for you today, last semester, if you happen to catch it, we actually showed how math shows up in some art. Well, I didn't mention one of the most famous artists who is known for his mathematical influences, so I was going to show you some works from him today. His name is M.C. Escher, and he was a Dutch artist, and I think he died just 30 years ago or so. And you might have even noticed some of his drawings and paintings without even realizing who it was. So I brought a little selection of some to show you today, and I'll show you a little bit about how the math is involved, and then we'll get right to some math questions people have asked us. So I brought my little laptop here with me. I'm going to show you a few things I've dug up, some of his more famous paintings, or I don't know if they're paintings, they're more like drawings. The first one here, you might have actually seen before. It's a suggestion of infinity. You might think there's no math here, but many of his works actually involved infinity, and this one shows a hand drawing another hand, sort of a infinite loop that goes back and forth. You might see some of his images, by the way, in, I've seen them in TV shows, video games even. I've seen them in music videos. You'll see them on t-shirts. So if you see anything familiar, that might be why. These images tend to crop up all over the place. So I'll show you a couple others. That was one of his more famous ones. But he liked the idea of infinity, which obviously is tied to math. So I'll show you a couple other versions of how infinity showed up in some of his drawings. This is a little picture where you actually see the two shapes intertwine. In the middle, you see the dark horses on the top and the gold horses on the bottom, and then in the middle they sort of cross paths. It's a suggestion of a Mobius strip, and that's an infinite surface that has only one side. And we've actually done it on the show before. Maybe in the future we can do it again. He's got a couple other versions of those. Here's another one where these, I guess they're swans, perfectly intertwined in the middle, but almost looks like an infinity symbol. Again, looks kind of like a Mobius strip. This is actually a Mobius strip as well. I don't know if these are supposed to be like flatworms or what, but they made a little image out of these guys kind of winding through each other in an infinite loop. And this is a genuine Mobius strip here being crawled on by ants. And we'll see a little later in the semester perhaps what the Mobius strip has to do with some math. But here you can think of it this way. If the ants keep walking around, there's only one side to this thing because they keep going on the inner and outer edges of it, but they never cross over the edge. They just go in an infinite cycle over and over and over. He also liked tiling, and you might think like, well, what does that have to do with math? But actually there's a whole area of mathematics that studies symmetry and patterns, and they call them tilings. In fact, it's been proven that there are 17 unique different arrangements that these things can have. So M.C. Escher was quite interested in this, and he made a lot of different works of art off these. So I'll show you a few here. And it's interesting how he got the same shape to repeat in different positions and then all interlock just perfectly. So these are just a few I've dug up. He has many, many more if you want to check out some more. And he was also interested in, well, here's a tiling. This is, it's not perfectly uniform. It actually shrinks the size towards the center. Sort of a cross between the tilings and a suggestion of infinity. Here's another one where they're large in the middle and they get infinitely small at the edge. It's another similar one. He also very much liked geometry, and this is, I just brought a couple that show how he used geometry in some of his art. This one, I think technically this is a dodecahedron. Sounds fancy. It's a 10-sided shape, and it has a sort of sunken-in convex edges. And then this is just a sort of intertwined spiral that I thought looked interesting. One of the things you'll definitely notice if you look through his work is that he loved illusions. And I don't know if you directly see mathematics, but there's definitely some perspective in here. And if you look at this carefully, the ladder is actually impossible. On the bottom, the ladder is inside the building, but then somehow on the outside, or on the upper level, it's on the outside. And he likes to just play with perspective and things that could never exist actually. But in the drawing, if you look at the top and bottom separately, it works just fine. I'll show you a couple others. This one's a famous one. If you look carefully at the staircase, I don't know if you can tell on my computer picture, but the staircase goes around and it goes uphill the entire time. So all four sides of that staircase look like they're going uphill. It looks like these guys are just walking uphill forever, which it's in a closed loop, so that wouldn't really be possible. This one I've actually seen in The Simpsons as well as some other TV shows. So this one is, well, if you look at the staircases, this one, they look upside down and all different perspectives, but if you look out the windows, he just has sort of, I don't know, rearranged the world a little bit to look different from different perspectives. And this is the last illusion I was going to show you. This one, if you look carefully, it shows a waterfall that it comes down on the left, but then it winds downhill to get back up to the beginning of the waterfall. So it's almost like a water that flows downhill forever and ever. So that's not very possible in real life, but it looks pretty cool. So my last work of art from M.C. Escher to show you. He made several of these really long, almost mosaics or something. He called them metamorphosis. This is actually the third one. And I had to download different pieces of it and glue them together on my computer because it's so large. But I was going to show you really quick. It's really interesting. He starts with these sort of checkerboard, and he slowly morphs the shapes throughout the whole picture here. And if you go through it, just slowly morphs from one thing to another. It's these tilings we talked about. And he goes through this whole transition. I'm going to speed it up here a little bit. And we're only halfway through. We're not even halfway through at this point. So he keeps going through all these different shapes that all interlock and slowly drift. And in the end, he's going to wind back right up at the chessboard and back to where he started. So want to see it in reverse really fast? OK, watch close. Here we go. End to beginning. So if you want to check out this for yourself, this is the official MC Escher website. This is it's just mcescher.com, no period after the M and the C, just mcescher.com. And you can actually check out many galleries of his prints there. And actually, this is a game show that hasn't been around for a while. It's an old game show called Let's Make a Deal. And it was hosted by a guy named Monty Hall. And the way it would work is if you were on this game show, you would win some prizes throughout the show. And at the end, sometimes he would offer you a deal to trade your prize in for something else. So we're going to pretend that we're playing this game show. And today's contestant is an official friend of the Math Line. Christina. Is her birthday today, so happy birthday, Christina. And she's going to be our contestant today on the game show, and I'm going to be your host. So I'm Monty Hall for the next few minutes. So the way it would work is Christina would have won some fabulous prize throughout the show, you know, new sofa or something. And at the end, I might offer her a deal. So I might say, okay, would you like to keep the prize you won, or would you like to trade it for a new prize that I have hidden behind 3 doors? So he would have prizes behind doors or behind curtains. And usually what happened is there was one really good prize, like a new car, and then 2, well, kind of loser prizes like a goat or, I don't know, cherry pie or a bag of trash or something in general that you probably didn't want. So you were hoping, of course, to pick the door with the car. Well, I didn't have time to build you some doors, so what I did is I brought 3 cups with me and I numbered them, and I have prizes hidden under the cups. So you're going to pretend that we're playing with the secret doors. So our contestant Christina has decided that she cannot resist the temptation of the surprise, so she's going to trade in her prize and hopefully get maybe a new car. So what happened is she'd pick one of these doors. So let's say Christina picks door number 2. Okay, so now me as the host, I don't immediately reveal what she has won. So she wants to, of course she wants to know if she won the car or not. I'm not going to tell her right away. What I would do is I would pick one of the other doors and show her what she didn't win. So I'd say, okay, well, you didn't pick door number 1, so you didn't win. Okay, today we have a frog. Great. So Christina's probably happy because she's thinking, well, good, I didn't pick that one, so I still have a good chance of winning the car. So then I would say, okay, Christina, would you like to keep the door you chose? Or I'm going to give you one last chance. Would you like to change to the other door? And Christina would have to think about it. And on the show in the past, many of the contestants would change, and many would keep the original door they chose. So the question I have for you is, does it make any difference? And I don't know about you, but my logic first says no. I mean, all the doors have an equal chance of having the car, so it's just a question of luck. Do you feel lucky with the door you first chose, or I don't know, do you feel like you should switch? Well, an interesting thing happened. If you watched a bunch of the shows, those who chose to switch to the other door won more often than the ones who didn't. Maybe a coincidence, right? Well, you could try this little game with your friends. You could do just what I did here and do it a whole bunch of times. And I bet you anything, if you do it enough times, those who switch will win the car more than those who don't switch. If you're really dedicated, you can actually find that people have written Java applets on the web that will simulate this game. It's become a very famous math problem, actually. It's called the Monty Hall problem on most websites. So, and Monty Hall, by the way, Monty is spelled M-O-N-T-E. So if you just go to Google and search for Monty Hall problem, I guarantee you'll come up with a bunch of websites. And some of them have little programs, and they will simulate the situation. They'll randomly pick a door that has the car. They'll randomly pick which door you choose. They'll trade or not trade. They'll see if you win the car, and they'll keep track. Guess what happens? If you switch, you win the car a lot more often than if you don't. So this is very counterintuitive. I'm going to show you a little bit of the math behind it. And the fact is, you can mathematically prove that you will double your chances of winning the car if you do switch. Why would that be true? And this doesn't seem to make sense with your intuition. Well, if you think about the original situation, I'll give you a general idea of the math. We're playing with probability here. And when you first chose that door, Christina chose door number 2. there's a 1 in 3 chance you have the car. A 1/3 probability you chose the car. And of course, that's true for any of the 3 doors. So what changes when you might switch your vote later? Well, what changes is me as the host, I show you one of the doors, and I know where the car is, so I'm not, of course, not going to reveal the car. If you've chosen the car already, I could reveal either of these other doors and show you one of the less desirable prizes. If you have not chosen the car, then it would have to be, if you didn't choose it, it's in number 3, and I'm not going to show you number 3, I'm going to show you number 1, because I don't want to reveal the car. So either way, I'm not going to show you the car, but that actually changes the game. And here's how you can think about it. When you chose door number 2, 1 out of 3 chance. What are the chances that you didn't pick the car? Well, there are 2 doors you didn't choose, so your chances are 2 out of 3 that you didn't pick the car. But if I let you switch later, you in effect get to switch to the 2 out of 3 doors. You in effect get to take a pair of doors, because I am going to show you one of them. So by you switching, you are actually choosing both doors. I revealed one of them, you're going to take the other. You are switching from a 1/3 probability to a 2/3 probability, a double percentage chance that you can win the car. So if you ever get on a game show like this, of course, unfortunately it's off the air, but if you did, you should always switch to better your chances of winning a car. So for example, our little game here, Christina chose door number 2. She would, she took my advice. She would switch to door number 3, which is the one we have not revealed. And of course, inside door number 3 is a brand new car for you. Hopefully yours is a little bigger than mine, but there would be the car you won. Now, if she would have stuck with door number 2 and decided she didn't want to, change her initial choice, she would have won today a nice little dog. That's not a bad prize, but it's a stuffed little dog. So I think the car would be a little better. Okay, so interesting thing about this story. There is a newspaper column, I think it's in the Parade, is called, by Marilyn Vos Savant, I think is her name, and she is listed in the Guinness Book of World Records as the smartest woman in the world. She discussed this, and she gave the same conclusion we just gave you, and people wrote in, they were all mad that she was wrong. Even mathematicians wrote in and said she was wrong, and of course, she's not wrong. She was exactly right. It's just kind of counterintuitive. I don't know if you saw a previous episode, we actually talked about a game show. There was this old game show called Let's Make a Deal. And we talked about how some of the prizes work, and there was actually some math that came into it. Well, there's this new game show on now. It's called Deal or No Deal. And it's on NBC, and they're running it, I think, every night this week, and I think it's running next week as well. And I caught an episode of this, and I thought there was some interesting math lying underneath there. So I was going to show you a little bit about the math involved. The game is very simple. In fact, I was going to show you how it works. And to do that, I went to NBC's website, and they have a sample version you can play on the web. So I brought my computer in, and I'm going to show you. We're not going to play the whole game, don't worry, but I'm going to show you a little bit about how it works. So if you want to have a look at my screen with me here, this is a layout of what the thing looks like. And what is happening here is there are 26 suitcases, and each has a different amount of money in them. And if you can see all these little amounts on the sides here, they start with a penny here, and they go all the way up to $1 million. So the first thing you do is you would pick one of these suitcases to be your suitcase. So for example, I'm going to pick lucky number 13 here. And what happens is I don't know what's in here, but the way the game works is if I wanted, I could just take number 13 home with me right now, and I get whatever money's in there. So you might think, hey, well, that's fine. Maybe I have $1 million in there, but then again, maybe you have a penny. So, that wouldn't be very fun, right? The game would be over too fast. So of course, that's not what happens. What really happens is they now have you open some more suitcases to see what you didn't pick. So right now it's telling me I have to open 6 suitcases. So I go over here, and for example, I just clicked on 22, and this $1,000 just grayed out. So I know there's $1,000 in that one. I know that's not in my suitcase. So I picked some more. That was 10,000. That one was a penny. That's good. I picked number 3 here. That was $5. I picked 14. That was 300,000. That's a bummer because I was hoping to get that one maybe. And 8 had $400. So here's the tricky part. Why are you doing this? Well, they have this mysterious banker that comes in and offers you some money. So the banker's saying right now, according to this little computerized version, I will give you $33,706 for your suitcase. So obviously you can't open it first. So the whole question is, should you sell the banker your suitcase and take home $33,000 right now, or should you take a chance and see maybe what is in your suitcase? Well, what usually happens is if you keep playing, by the way, this is where they come in and say that, is it a deal or no deal? And if you say it's a deal, you take the money and run. If it's no deal, then they're going to make you open more suitcases. and then the banker's going to make you a new offer. So here's where the math comes in, because so far, right, it's just all luck. I mean, you didn't have any skill in picking your suitcase, and you don't have any skill in picking more suitcases. That's all luck. Where this comes in is trying to weigh the banker's offer. So, you know, if you watch me play, if we play this some more, let's say I opened up a bunch of low amounts, that means that there's more possibilities, more chances that I have a really high value in my suitcase, and that makes it more valuable to the banker. So I actually caught an episode of this last week, and I took some screenshots, and I'm going to show you this is what actually aired, and you'll see an actual game happening, and then you can see what the banker's offers do. And the math that I wanted to ask you about is, do the banker's offers seem good? I mean, is he being fair, or is he trying to take you for a ride, and, you know, and should you do it? Of course, that's all part of the game. That's where it actually becomes fun. So back to my computer here for a second. I'm going to show you. I have some screenshots here. This is the guy who was playing, and he opened 6 suitcases, and if you can see, there's some that are dim. Those are the ones he opened, and he actually did pretty decent because he opened a penny and $1. And unfortunately, he opened one for $400,000, so he knocked a big value off. But the bank offered him $17,000 for his suitcase, and he said no way. I'd probably agree with him. I think you have, you know, a lot more chances of getting a higher offer. So after that, he had to open some more suitcases, and the next one he had to open, I think, 5 more suitcases, and then the bank offered him $22,000. And if you look, he still has a lot of high amounts on the board, so he didn't go for it. He kept playing. Next one, he had to open, I think, 4 or 5 more suitcases, and you can see he still has some big amounts left, although he did lose the $1 million one. He was pretty bummed, if I remember right. But the bank offered him $35,000 for a suitcase. He said no way. So now he had to open some more, and he's thinking very hard, as you can tell. He knocked off some of the big amounts, but he still has $500,000 here and $750,000, and the bank offered him $68,000. So you got to think about that. I mean, you could take $68,000 right now, even if you have, you know, a tiny amount in your suitcase. You would walk away with $68,000, and the banker would be stuck with, you know, the lousy amount you had. But he said no. He said no deal. He kept going. So here's what happened next. He got an offer of $125,000 because he knocked off some lower amounts. So the bank, it made it look, you know, it was a little more desirable to the banker, so he upped his offer. So the guy could have walked away right now, $125,000. He said no. He kept going. He had to open a couple more suitcases. Luckily for him, he kept these 2 high amounts on the right here, and the bank offered him $199,000. He still said no. Here's what happened next. He knocked off a couple lower ones. He kept these 2 high ones. And then if you look on the average, he has a 50-50 chance that he has either $500 or $750. So the bank offered him more. They offered him $279. He still didn't take it. One more time, he opened 1 suitcase. Luckily, he knocked off one of the low ones. He kept the 2 high ones. The bank offered him $359. He took it. So what I wanted to ask you, this is where the math comes in. You know, there's always a little bit of judgment. You know, is this a good deal for me? I mean, I think I would have probably taken the money run before he did. But was this a good deal? And you can look at this from 2 ways. Is it, you know, you can look at it from the contestant's point of view. Are these good odds, and should I get out now? And you can look at it from the banker's point of view. And, you know, it's a show, so I'm sure it's all just part of the, you know, the fun of it. I don't think it's a legitimate banker. They're trying to make a good investment. But just for the sake of argument, let's say it was. Then the idea would be, is this a good investment? Is he, you know, are these amounts he's offering wise? So what I thought we could do is just take that very last one, and I'll show you how the math would work out. And this is more from the banker's point of view. From the contestant's point of view, he had a 2 out of 3 chance of having a high amount. So, you know, in the end, he actually came out pretty good odds. But from the banker, this is actually involving a little bit of mathematics called, it was part of probability, it's called expected value. And the idea of this is, if the banker were to play this game over and over and over, in the long run, would this be a good deal? So here's how it works. There's only 3 amounts left there. One of the amounts was in the suitcase, and the whole question for the banker is, you know, how much should I offer to make this worth my while, worth my risk? So I thought what we could do is I'm going to go on my little math cam here. I'm going to show you the amounts he had, and we'll see what kind of deal this would be for the banker. So remember, the banker offered $359,000, and there's 3 scenarios here. So under scenario number 1, all right, what would happen here? He's going to pay $359,000. But he's only going to get, you know, the first amount he had was $25. So he's going to pay that much. He's going to get $25. Of course, this is a very bad deal for the banker. But this nets him negative $358,995. Not so good. So that's this would be his loss, basically. He would lose $358,000 if this scenario happened. Under the second scenario, that was the first one, he would pay the same amount, but he would get, well, the other amount possible was $500,000. So he would get $500,000. For him, that's a net of $391,000. That'd be a good deal for the bank, of course. And finally, under the third scenario, he would get $750,000. So even better for the bank. So that would net him, if you subtract out the $359,000 he had to pay, that would net him $390,000. Or sorry, this is $391,000. I lied on this one. This is $141,000. I did these ahead of time so I wouldn't have to do it in my head, and I looked at the wrong one. So here's how the mathematics works. These are 3 scenarios, and they're all equally likely because it's a 1 in 3 chance for any of those to be in the suitcase. So what the banker would do is say, all right, I have a 1/3 chance of losing this $358,000 here. I have a 1/3 chance of actually winning some money, which would be the $141,000. That's if he gets the $500,000. And I have a 1/3 chance of getting $391,000. And this produces an expected value. You can almost think of it like this. This would be an average amount he should win in the long run if you play this game over and over and over. So I figured this out, and it turned out this gave about $57,000. So actually, this is it's in the banker's favor, this offer he made, which might sound surprising because he is taking a risk. But remember, it's in his favor in the long run if the banker does this over and over and over again. And, you know, in just one shot, he's taking a risk. Well, as it turns out, the guy took the money and ran, and he had $25 in his suitcase. So he made a very smart move. I don't know if I should say smart. How about lucky move? The banker paid $359,000 and was stuck with the $25 in his suitcase. So he lost out this time. But in the long run, you know, the banker, I noticed he was making numbers were always in his favor. And just for fun, what I decided to do is I went through all the offers the bank made and figured out how close he was to the expected value, the real value. And it turned out that in the beginning he was making very low offers. In fact, in the beginning I checked he was making like a 12% of what the average expected value should be. And he kept increasing as it went. And I'm sure they do that so people don't bail out too early because that, you know, makes the game less fun. So he went from up to like 20%, 40%, 60%, and finally by his last offer, it was like 85% of the expected value. So the bank was actually getting, not quite fair, but he was getting decent offers. So anyway, if you want to play yourself, you can go to NBC's website or you can check it out on TV. It's on every night this week, I think, and like I said, I think it's next week as well. For today, you know, we have all this Halloween stuff because we went crazy in the studio, and it would have been so much nicer if Halloween were on a Wednesday, but it just happened to be on a Tuesday this year, so we missed it by 1 day, but that's okay. I told you the fun never stops here. So, but I actually have, as you would guess, I have an equation that will tell you what day of the year any date will show up on the future. And I know you can probably go on your computer calendar and, you know, look into the future and find out, but that's no fun. This is much more fun, right? So I'm going to show you the equation. This is it's called the Zeller congruence. And if you look at my equation, there's actually some funky looking symbols in there, but that's okay. I'm going to explain exactly how this works. And what I thought we could do is we're just going to pick a date. I picked 2012, and we're going to see what day Halloween is on 2012. So I'll show you how this equation works. I have a copy over here on my math cam, so we'll work on that. And there's a bunch of variables in here, but don't worry, we're going to figure out exactly what goes on. So I've got the equation written here, and you know, these little guys, I keep trying to shoo them away, and they keep showing up. So anyway, here we go. Get out of the way there. So here's our equation. There's all this crazy stuff going on in there, and I don't know if you can read my small type, but M is the month, and it's numbered funny if you look. It actually starts 1 for March. It doesn't start 1 for January. There's a reason behind this, and what this equation is doing, it's actually kind of clever that they can do this because you have to count for leap years. And I don't know if you knew this, but every 100 years or whatever, they eliminate a leap year. This is to make sure the calendar stays in sync with the actual sun rotations and all that. So it has to account for all those things. So that's why things are a little funny. So M is the month, and if 1 is for March and 2 is for April, etc., that means October is an 8. So M is going to be 8. I'll put a little 8 there. Y is the last 2 digits of the year. And I mentioned we're going to do 2012. So Y will be 12. And C is the first 2 digits of the year. That'll be 20 for 2012. D is the day of the month. We wanted Halloween, so that's going to be the 31st. And then X is the result, and that's going to be the day of the week. And if you look how this works, it's numbered for 0 is Sunday, Monday is 1, Tuesday is 2, etc. So when all is said and done, you're going to get a number 0 through 6. And this equation is actually going to tell us exactly what day Halloween will be, 2012. So I'm going to go ahead and work out this crazy equation here. And there's some funny symbols in here. I'll explain what those mean. But first I'm just going to put in the numbers, okay? So the first thing we have is 13 times m, which is 8, minus 1 over 5. And I have these funny brackets around it. And then we have y over 4. Y was 12. And then we have c over 4. C was 20. All right, and then we have plus d, that was 31. And then we have plus y, that was 12. I'm almost out of room here. And then minus 2c, c was 20. So what are these funny looking brackets? This is a special function called the floor function. And all it means is you have to round the number down to the nearest integer. So for example, if you compute out this little fraction here, you get 20.6. So those brackets mean you always round down. So this is going to be 20. All right, 12 over 4 is 3, and it's already rounded, so I don't have to worry about anything with that. 20 over 4 is 5. That's already rounded, so I don't have to worry about that. 31 plus 12, and then minus 40. Okay, so I did this all, and I got 31. And now if you look at my equation back here, it was hidden behind my head. It says mod 7. What the heck does that mean? Well, this is actually, you probably wouldn't see this term for quite a while in your math classes, but that's okay. It's not too hard to comprehend. Mod 7, it's short for modular, and what that means is we want the remainder after dividing 7 into it. So what you have to say is, okay, 31, 7 goes in 4 times, that makes 28, and the remainder is 3. So the answer to this really is 3. So if you go back to my, my list here, what does that mean? Well, X is the day of the week, and 0 is Sunday, Monday is 1, Tuesday is 2, Wednesday is 3. So this is, means in 2012, Halloween will be on a Wednesday, which is perfect for us because our program is on a Wednesday, and that means when you tune in 6 years from now, it's going to be Halloween, and we're going to have all kinds of fun. I'm just kidding. It's probably going to be on a Wednesday sooner than that, but you know, I just kind of picked a random year, and hey, this one worked out pretty well. So, you know, I know you can go on your phones or your computer and figure this out, but hey, maybe this is how your phone and your computer are actually doing it themselves. Maybe they're just using this equation, right? All right, well anyway, so if you want to play with that, you can actually plug in any date from the future or past. It'll tell you what day of the week it's on. So, I don't know, you can see what day you were born or when your 100th birthday is going to be or something fun like that.